How's it going, guys? Mr. Caselli just told me that you guys were having some audio issues, so decided to re-record this. I'm also going to take the opportunity to show you the side of the notepad that was cut off last time. I kind of jumped over some things because the sides were cut off, namely at the very beginning. I included f of b minus f of a over b minus a for our slope equation. I also, if you didn't get the discontinuities, two different kinds of discontinuities, you might want to pause the video and make sure you have that in your notes. And then last thing I mentioned was how to find the horizontal asymptote by finding the limit of f of x as x approaches plus or minus infinity. Okay, so picking up where we left off, uh, answering questions 19 and on. I'm just going to go ahead and erase this. I'll leave these formulas here, these exponent rules. I'll just walk you through these one more time. Okay, I'll even go through the rule one more time. Any number raised to a rational exponent, the denominator, that is our root. So that sits here in this pocket of this radical symbol. And the exponent the numerator of the fraction remains the exponent, either inside or outside of the radical, whichever one is easier to solve or more convenient. And any number raised to a negative exponent just means 1 over that expression where the exponent becomes positive. Okay, so let's use those rules and see if we can answer questions 19 through 24. So we're just going to rewrite this as x to the 3/5 plus 2x. Now, because 2x is inside the radical, we're going to rewrite it like this. Okay, same thing here. We're just going to rewrite this as x plus 1 to the 1/2. We can rewrite this because the radical is in the denominator. That means that the exponent must be negative, and it's just like question number 20. So this has to be x plus 1 to the negative 1/2. Being able to do this is going to be crucial in calc when we start taking derivatives and integrals and stuff. Okay, same thing here. This is x to the negative 1/2 minus 2 times x to the negative 1 because our x is in the denominator here. Moving right along. Notice this 4x is not in parentheses, so only the x is cubed. So this remains a fraction where the denominator is 4, and we have x to the negative third power. Plus, same thing, 1/2 x to the 3/4 power. Remember, the root is the denominator of your rational exponent. Again, this is 1/4 x to the negative 1/2 because the square root is in the denominator. Minus 2 parentheses x plus 1 to the 1/2. And we can do the same thing in reverse here. I'll leave that up to you. That table, I'm just gonna leave it where it is. It's not bothering anybody. Just a little janky, but we'll be okay. Just remember um, how to convert from degrees to radians from algebra 2 and pre-calc. And remember that any point on the unit circle with radius 1, has coordinates cosine theta, sine theta. So when you look at the unit circle, you can use those x values for cosine, y values for sine, and match them up with the radian measure for each of these questions. So for example, sine of pi over 6. Pi over 6 is really 30 degrees, as you can see here. So sine of 30 degrees is 1/2. So I'm going to use the table and 1/2. All of these questions can be solved using this table. So I'm going to skip the cosine, sine, tangent. I'm going to talk about the secant. Please remember your reciprocal trig functions. Cosecant of theta is equal to 1 over the sine of theta. secant of theta is equal to 1 over the cosine of theta, and cotangent is equal to 1 over the tangent of theta. Because tangent of theta is sine over cosine, therefore cotangent of theta is cosine over sine. Okay, so just remember that. So let's look at secant of pi over 2 to solve that. Remember the secant is 1 over cosine, so we can think of this as 1 over the cosine of pi over 2. And then we just need to find that on the table. Remember, pi over 2 is 90, and the cosine of 90 is 0. So this is 1 over 0, which is undefined. Okay. Let's pick one of these, 43, 44, or 45. Uh, question number 43. Please remember that sine of x is 1/2 at 30 degrees. So if I were to draw that on our unit circle here, 30 degrees, sine, so this would be cosine of 30 degrees, sine of 30 degrees. Sine is the y value. So that means that on our unit circle, there exists some other point over here in quadrant 2 that shares the same y value. So therefore, solving this sine of x equals 1/2, we actually get two solutions. We get x equals 30 degrees, or pi over 6 if you want to stick to the radians, and 5 pi over 6. Okay, and the way that I'm able to determine what this angle is, please remember your trig uh, quadrant rules. So I'll scroll over to the right. Uh, please remember, if our angle is in quadrant 2, then our reference angle is equal to 180 minus the given angle. Or if you're using radians, it's going to be pi radians minus the given angle. To determine this other angle on the other side, if we were to choose that as theta, so I'll draw that red. If that's our angle theta, then the other angle in quadrant 2 must be 180 minus that angle. Similarly, 180 minus the reference angle gives us the given angle. So we know the angle here must be 30, and 180 minus 30, which is 150, or if you want to stick to radians, it's 5 pi over 6. Okay, please recall how to convert from degrees to radians. So an angle in degrees times pi over 180 will give you the angle in radians, and the angle in radians times 180 over pi will give you the angle in degrees. Okay, so we're using quadrant 2 rules because this is sine. We would use quadrant 3 rules for tangent and quadrant 4 rules for cosine. And I'll quickly remind you what those are. In quadrant 3, our reference angle is our given angle minus 180. And in quadrant 4, our reference angle is 360 minus the given angle. And again, you can use radians for that. Okay, so that's how I was able to find the other angle, 5 pi over 6. Okay, let's erase all of this. So solving these exponential equations, we have to remember just a few things. Well, they have is written here that e to the 0 power is 1. Well, essentially all numbers to the 0 power equals 1, and e is a number, so that's true. Natural log of 1 is 0. That's also always true. And over here I've written that for all real values of x, e to the x is positive, right? It does have a horizontal asymptote of y equals 0 when x approaches negative infinity, but it never actually reaches 0. There's no exponent that will give you 0. So it's strictly greater than. Okay, so to solve these, we're just going to use the properties of equality. First, subtracting 1, and now we have e to the x equals 2 minus 1, which is 1. And if you remember up here, e to the 0 equals 1, that means x must be 0. But if you didn't want to do that, if you wanted to solve this using inverse operations, you'd remember that the natural log of e to the x and natural log of 1, you would remember the natural log of e to the x is just x, so that cancels out. We're left with x equals the natural log of 1, and the natural log of 1 is 0. They gave us that. So you can use that as well. Same thing here. Subtract 5, you have 3 e to the x equals 8 minus 5, which is 3. Divide both sides by 3, and you get e to the x equals 1, which is the previous question. So we don't need to do all of this work all over again. In calculus, you're going to see a lot of questions like this, where one question, once you have the answer to that one question, all the following questions kind of rely on your remembering that one question. And that's how we can just say we know the answer to this is x equals 0. Okay. For question number 48, I wrote the exponent rule. Any number raised to an exponent and then that expression is raised to the exponent again, we must multiply the exponents. So using that rule in reverse, we can rewrite e to the 2x as e to the x squared equals 1. Square root both sides. We get e to the x equals plus minus 1. But remember, e to the x must be positive. So we don't really need this plus minus. And then we can solve for x the same way we solved previously. X must equal 0. Now you could have definitely directly substituted following a hunch. Definitely want to use your hunches in calculus, especially around numbers like 0 and 1, the multiplicative and additive identities. So plugging in x equals 0, we get e to the 0 equals 1, which is true. So x does equal 0. We could have done that not so analytically. Okay, natural log. If natural log of e to the x cancels out, e to the natural log of x cancels out as well. And we're left with x equals e to the 0. And remember, e to the 0 is 1. Okay. Here I'd like to remind you of a clever algebra trick, and that involves taking this value and swapping it because we have a binomial difference on one side. Because I'm subtracting 3 minus natural log of x equals 3, I can swap those and I get natural log of x equals 3 minus 3, which is 0. Okay, if that wasn't obvious, I'll walk you through the steps. If we subtract 3 from both sides, so I'll erase it. We get negative natural log of x equals 0, and multiply both sides by negative 1. You get natural log of x equals 0, and natural log of x equals 0. Well, x must be 1 using this highlighted bit here. If you wanted to solve it and prove each step, you would exponentiate, and now x equals e to the 0, which is 1. Same thing here. Let's exponentiate to cancel the e and the natural log. We get 3x equals e to the 0. E to the 0 is 1. So dividing both sides by 3, we get x equals 1/3. Okay. 52. They want us to solve these equations. This is a quadratic. So please remember how to factor polynomials. This one does not have a c value, so this can be quickly factored into x, and x minus 3 equals 0, giving us our solutions x equals 0 and 3. Here we have to factor out, just like we did here, we need to factor out e to the x. And we're left with 1 plus x. And now we're going to do the same thing. We're going to apply zero product property like we did in the previous question. But again, remember, e to the x is strictly positive. It cannot be 0. So we can eliminate e to the x as a possible 0, or a possible factor that equals 0. And we can just simply solve 1 plus x equals 0, arriving at x equals -1. E to the 2x. Again, we're going to exploit what we did in question number 48. The rule here that says we have to multiply the exponents when a exponential expression is again raised to an exponent. So we'll do that again. That'll allow us to rewrite e to the 2x as e to the x squared minus e to the x equals 0. And here we can factor out e to the x. So e to the x, e to the x minus 1 equals 0. Again, e to the x cannot equal 0, but e to the x minus 1 can equal 0. That means e to the x must equal 1, and that means x must equal 0.